Now, how should you go about this? Here are some 4 general steps that you should look at. And the first says, before you're considering any upgrades in equipment, optimize the operation of your equipment through tune-ups, repairs to installation, and preventative maintenance. The economics of upgrades with new equipment or radically changed equipment are um, somewhat questionable if you're starting with a bad baseline. And that, of course, is the next step, create a performance baseline. Once you've got everything running up to par as best it can with the equipment you have, collect data on your production rates and energy consumption, your operating schedules, if you have a fuel-fired furnace, flue gas temperatures, an analysis, losses due to various components of the furnace, and then run an energy balance, and I'll show you how that's done later on, to highlight the magnitude of the losses. And what we're trying to do here is see how well you're doing overall and also see what factors um, give you the greatest potential for improvement. And when you reach that point, now you have a fair idea of what you want to go after in terms of energy savings. Start looking at the various types of improvements, and this may be equipment related, preheating your combustion air, adding furnace pressure control, upgrading your controls for the equipment, and do them individually, but also do some of them in concert with each other. Sometimes the sum is greater than the parts. Finally, once you've done that, then select the improvement or combination that gives you the best payback potential. Now, baselining is something that's not done often enough. It's a lot easier with electrical equipment than it is with fuel-fired, simply because it's a lot easier to put a meter on electrical equipment and monitor it for a period of time to see just what it's consuming. Where you have a hard-piped fuel supply line to a furnace, it's difficult to convince people that they've got to put a meter in, plus the fact that the meter itself is going to be an expense, and a lot of people don't want to have one on each individual piece of equipment. If that's a situation you're in with multiple pieces of equipment, create a portable meter set and insert a spool piece into the gas lines to each furnace or oven, and so that you can put this thing on one piece of equipment, monitor its consumption for a while, then take it out, move it to the next one, and just keep making a round robin until you have all your pieces of equipment covered. Now, this is what's known as a Sankey diagram, and if you've been in the industrial heating business for any length of time, you're probably very familiar with it. If not, simply it's a graphical representation of where the heat flow is in an industrial process. And the idea is that the width of the arrows is supposed to represent the size of the heat flow. So in this case, we're talking about BTUs or joules or kilocalories or whatever. That would be our unit of measure here. And this bears some looking into, because this gives you a very, very good graphic representation of what's going on, and I think most people can fix it in their minds. Typically with equipment, when it's first designed, everybody starts at the right and goes to the left. They determine the amount of heat that they need to satisfy certain loading conditions. Of course, this is determined by the product that you're heating, the temperature you heat it to, and the production rate. Once that number is established, then you have to go back and start adding in various losses that are going to occur in the process. For example, if you look above the output to the load, you see wall or conduction losses, opening or radiation losses. Down below it, you may have conveyor losses if a conveyor is extracting heat from the process, and heat storage, which is the heat that's actually placed into the structure itself as the thing is heated up to operating temperature. There's one other as well that doesn't show on here, and that's cooling losses. Many processes use cooling water. It's essential to the process, and heat carried out by that cooling water also has to be accounted for. When you add all those together, you get a term that in combustion is known as available heat. This is the amount of heat that you have to make available, to redefine it in its own terms, to satisfy the output of the process. If you don't do that, then the losses are going to get first priority, and your net output, the amount that you can heat, is going to decrease. There's one other major factor in fuel-fired systems, and that is the flue gas losses, because we are burning fuel. And so you have to add that in, and when you add that to the available heat, you get what's known as the gross input, and that is the amount of energy you have to purchase to run that process at that rate. Electrically heated systems are a little bit simpler simply because we don't have to cope with the flue gas losses. And so the amount of energy is essentially dedicated to the net output to the load, plus heat storage, conveyor loss, radiation and wall losses, and cooling water if you happen to have that in the process. Radiation loss is defined as radiant energy that comes out of any available opening inside that process heater. For example, if you have a large aluminum melting furnace and you open a door, a great deal of heat is lost by the interior surfaces, the refractory and the surface of the metal, losing heat by radiation to the outside. In some cases, this loss is pretty much deliberate because you have to open a door to charge a furnace, for example. In other cases, there are openings in various furnaces that probably could be closed up most of the time, and they just extract a constant loss. And at high temperatures, say above 2,000 degrees F, the magnitude of these losses is really quite great. It's surprising how much there is, even for a relatively small opening. Wall loss is the amount of energy that's conducted through the wall insulation and is lost off the outside skin of the piece of equipment. And so obviously you've got a lot of heat trying to get out. The purpose of insulation is not to stop that loss entirely, but simply to act as a filter to reduce the flow to the outside so that when it does get to the outer skin, the amount of heat that's actually taken away is relatively small by comparison. To give you an idea of different refractory materials, this is a graph that shows in generic terms the relative amount of heat that's lost through a wall for some fairly common constructions. The 9-inch hard fire brick bar on the top you can see is far and away the greatest loss. There was a time when people would build furnaces like this. It isn't being done now, fortunately, because the reason is that the losses are so great, it impairs the efficiency. It also makes the furnace a very difficult thing to work around because the high temperatures are on the outside. If you back up 9 inches of hard fire brick with 4.5 inches of insulating fire brick, you can see that you knock the heat loss off the walls down to about 25%. If you add an additional 2 inches of block insulation, you take it down even farther. In some cases, the existing lining is still good. People don't want to tear it out and replace it to put something in behind it, so they'll put a veneer of ceramic fiber over the fire brick. And you see a case here where that same 9-inch fire brick with 3 inches of ceramic fiber veneer loses less than half the heat of an unveneered wall. And then finally, down at the bottom, we have a 9-inch thickness of ceramic fiber. That obviously is the best of the available insulations, and if you have a situation where you can use it, where you don't have considerations of wear or gas leakage keeping you from doing it, you can see that that's obviously the best choice for wall losses. Conveyor loss describes the amount of heat that's taken out by your material handling equipment. Now, the graphic we have here represents it as a conveyor belt running through the furnace and exiting the furnace at the discharge end, and then returning outside the furnace or underneath it back to the entrance end, and then it goes back in. And of course, the problem with this configuration is that as a conveyor passes through the furnace, it absorbs heat from the furnace. As it comes out and makes its return pass underneath, it gives up a good deal of that heat to the outside room, and then it has to be reheated again as it goes back through. Now, for things like conveyors, the most logical approach is to take the return pass of the conveyor and keep it inside the furnace structure itself so that it doesn't cool off. There are other types of conveyors as well. For example, in large heat treat and forging operations, car-bottom furnaces are used very frequently for heavy loads, and that car is tons of refractory and steel, and it has to be removed from the furnace periodically so that you can take off a hot piece and place cold ones back on it. While it's sitting out in the room, it's going to be losing heat. And there are other types of conveyors as well, but you get the idea. It's your material handling system that's extracting heat from the system. You want to try to minimize this.